Hello, Integrated Math 3 and Integrated Math 3 Plus. Welcome to lesson 13-3. We were talking last time about inverses and compositions of functions and how inverses undo each other, so that when you did a composition of two inverse functions, they canceled each other out and you're just left with x, which is kind of magical and awesome. But how do we find these inverse functions, right? I mean, that's important. We talked about the coding earlier in the earlier in the unit, that there are two types of people who might receive a coded message. There are those for whom the messages weren't intended. You were supposed to get that message. It was meant for you. But of course, there are also spies who intercept the messages. Now, in that first lesson, you were the intended recipient, and so you had the information you needed to decipher the message. You didn't have to start from scratch. You didn't have to figure out what the code was. You just had to undo the steps that your friend had done. Now, one of the really important features of your friend's code that we did at the very start, and the reason we did it, is because it is what we call one-to-one. Each letter in the input alphabet is uniquely paired with exactly one letter in the output alphabet. So as long as you're careful when you're working backwards, you're never going to have to wonder. There's never any question as to what the original letter was, right? So if I was like, hey, let me play this for you. Boom, play my little thing. So we knew exactly what the pattern was, that it was off by 5. And so I was like, hey, if I've got an H, that should give me an M, right? We were working our way backwards through all of this. They gave us a B, so I was like, oh, well, so that goes with W. M goes with H, right? T goes with O. It's always one-to-one. And so as long as you're careful when you're working your way backwards, it really wasn't that bad, and you're not going to have issues with finding what the original message was. Now, as we went further into this, we were noticing that not all of our functions are one-to-one. So for example, we ended off the last lesson with these functions, a couple of these functions, and we noticed that when we graphed f of x equals 3x squared minus 5, that of course gives us a parabola, but a parabola is not a one-to-one function. If you were to draw a horizontal line, anywhere I draw a horizontal line, I should only touch the function once. Oops, sorry about that. Put it where it actually goes. Sorry, I'll fix that. So if I were to draw a horizontal line, boom, 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 it comes across, you see the problem is that it hits twice. If it's a one-to-one function, it should only hit once. So some of our functions are one-to-one and some of them are not. And so this guy totally failed our horizontal line test, which creates a whole host of issues in and of itself. We won't get into too much. The other thing we noticed is that when we did our composition of functions, we noticed that we got the absolute value of x. We didn't just get x. And so, yeah, it created some problems for us when we were simplifying because of that square root. So one of the first things you need to do is decide, hey, is my function a one-to-one function? If I graph it, will it pass the horizontal line test, or do I need to restrict the domain to make it one-to-one? Once you have decided it's a one-to-one function, you've looked at it and you're like, hey, that's a one-to-one function, then you can find the inverse. And we have a method for doing that. And that's what we're going to be playing with today's lesson. So to start off with, we have a little scenario going here. Cheerleaders are planning to sell some Spirit t-shirts to raise money for their squad. They've contacted a printing company. They've gotten pricing information. The problem is, and this is not uncommon, you've got to pay for the shirts in advance, right? You have to pay for the shirts up front, and then you turn around and you sell them. They've got $500 in their budget, and they want to figure out how many shirts they can order. Now we have this lovely table. This is the pricing table, the pricing information they got from the printing company. You have this table on your paper, on your student activity sheet 3. Problem number 1, its table is sitting right there. So I have a few questions for you, and we're going to start off with question 1 with part A and part B. So you've noticed that there's clearly a pattern of a constant addition here. Hopefully you've already caught that. You're like, oh, it went from 25 to 28 to 31 to 34. It looks like we're adding $3 for each shirt. Now, the thing is, we said we had $500, But if we tried to figure this out by making our table go all the way up to $500, we're going to be here a long time. It's going to take some time to do that table, and we don't want to do that. We want to spend time ordering the shirts and getting everything ready to go. So since we can clearly see there is a pattern of constant addition here, can you find a function that will model the cost as a function of the number of shirts? There's a few ways to do this. If you remember arithmetic sequences, you might be able to find a way to do this. Or if you remember from our lesson last time, we did our whole y minus y sub 1 equals m times x minus x sub 1. Remember we had this formula that we used last time where I picked a point to plug in, and I also figured out what the rate of change is, the slope rate of change is. So either way will work just fine. So I would like you to go ahead and do question number 1. Start off with part A. Find a function that's going to model the cost of the shirts. And then once you've done that, see if you can do part B. How many shirts can the cheerleaders order for $500? Go ahead and hit pause to work this out, and then hit play when you're ready to check your work. So I started off with the formula, and I did go ahead and use this formula because it was the one we used last time, and so it just made sense to keep using it. So I went ahead and used this formula, and I was like, all right, I'm going to use the easiest point. When x is 1, y is 25. Plug that in, x minus 1 and y minus 25. My rate of change was 3, right? Because this was a linear function. Add 3, add 3, add 3, add 3. So my slope is 3. So I went ahead and plugged that in. Distributed the 3, I get 3x minus 3. But if I add 25 to both sides, in fact, here, let me write it down. So I went ahead and distributed the 3. So I end up with 3x minus 3. And then, of course, I added 25 to both sides. So plus 25 plus 25, which means I ended up with this lovely little guy right here. So I ended up with y equals, I can do this, yeah. So I ended up with y equals 3x plus 22. And instead of a y, I just plugged in an f of x to make it a function. Yay. So here's my function, f of x equals 3x plus 22, and that gets me through part A. But part B says, hey, they've got $500. So tell me then, how can you use this function to figure out how many shirts they can order for $500? Hopefully you're already working on that. So let's see what you did with it. I'm going to erase this, otherwise it's going to get in the way when I go to the next page. Boo. Make that go away. Go away. It's gone. So we're going to move to the next page. There it is. So when I saw this 500 equals, I set 500 equals 3x plus 22. Hopefully you did a little bit of work there. So 500 equals 3x plus 22. They have $500 to spend, so I set it equal to 500. If I subtract 22, this is why I have a calculator handy, because dang, if I know that off the top of my head, I do know that off the top of my head, it's 478. I'm all acting like I don't know. I know. And of course, in order to get x alone, I do need to divide by 3. And of course, we don't have pieces of t-shirts, so go ahead and round to the whole number. This means that I get x of 159. I actually got 159.3 going forever, but like we were saying, this is what we were just saying, is that you wouldn't have 3s going forever. That'd be weird. So we're just going to say, look, I can get 159 shirts, and we'll call it good. So this brings up another issue, though, because one of the girls mentions, like, okay, with our $500, we could get 159 shirts to resell. But then one of the girls says, do we really need to use all of our money for this? Maybe we should only spend $300 on t-shirts. And another girl says, well, maybe $400 would be okay. So here's the deal. instead of working this function over and over and over again, right? Instead of doing 400 equals and 300 equals and doing this over and over again, there needs to be a more efficient way to find this, all right? To find the inverse. So we're going to go ahead and see if we can switch things, all right? We're going to see if we can switch our f of x and our x. We're going to switch our input and our output, because so far our input has been t-shirts and our output has been money, and that's made it really hard when we're going to find our input. So let's first of all decide, hey, is this function f of x equals 3x plus 22 invertible? Is it a one-to-one function? So this is question number 2 on your student activity sheet. Go ahead and pause and give it a few moments to think about whether or not this is invertible, whether or not it's a one-to-one function, and then hit play when you're ready to continue the discussion. Well, I noticed that this is a linear function, and this is not going to be a very good graph, guys. Let's just preface that. But if I were to graph this function, it's a line, right? And it hits my y-axis at 22, and it has a slope of a positive 3, so it's going to go up 3 over 1, up 3 over 1, right? All that. So this is going to be a nice, this is a terrible line. Pretend I did a better job because that's awful. So this makes a nice, lovely linear function. What this means for us is it a one-to-one function? Is this going to pass the horizontal line test? Anywhere I draw a horizontal line, is it going to touch once or more than once? Well, so far as I can tell, it's only ever going to hit it once. So to me, that says this is a one-to-one function. This is totally an invertible function. So if this is an invertible function, let's invert it. Is that the right terminology? I'm not even sure. We're going to find out. Erasing, erasing, erasing it all. There we go. Better. All right, let's see what we can do then if we make this an invertible function. So the idea is our original function f of x means that we input t-shirts and the output is the money, but we're trying to switch that so that our input is the money and our output is the t-shirts. So we've decided this is a one-to-one function. I should be able to find an inverse for it. So in order to find the inverse, we're going to do the composition. Remember how we said last time that a composition of functions would cancel each other out and just give you an x? So we're going to do that. So f of x is our original function, and we're going to call the inverse function g of x. And we're going to find the composition. So what this means is I'm going to just plug in g of x. I have no idea what g of x is, but I am going to just plug it in. Everywhere I see an x, I'm going to plug in g of x. Now, what did we just say about this left side? Last time we were saying that if they're inverses, f and g are going to cancel each other out, and you're just going to be left with x. Boom. Ooh, so now let's go ahead and solve for g of x. Let's get g of x all alone. You're going to use the same steps that you used earlier, right? So I'll start off by subtracting 22 from both sides. So that's gone. And I have x minus 22. And then I'm going to go ahead and divide everybody by 3 so that those 3's will go away. And there we go. We just found that g of x is 1/3 x minus 22/3. Yay! So what this now means is I could plug in 500 and figure out how many t-shirts I could get out of it. I could plug in 300 and figure out how many t-shirts I could get out of it. I could plug in $400 and figure out, hey, how many t-shirts am I going to get out of this? So this is terribly convenient. We are going to use our new notation since g of x is the inverse. Remember that we like to use our new notation that we learned last time, the inverse of f notation. So g of x is the inverse of f. So I can either write it as g of x or I can write it as the inverse of f of x equals 1/3 x minus 22/3. So for the original f of x, x was the number of shirts, but on my inverse of f, X represents the money that I have available to buy shirts. So keep in mind, these are our steps, right? This is how you're going to find the inverse function. If you've decided that that you have a one-to-one function and you want to find the inverse of it, fine. Write the composition. So we'll just use g of x, write the composition. Notice that f and g will cancel each other out since they're inverses and you just end up with x. And then solve for g of x. Get g of x all alone and boom, there's your function, there's your inverse. Yay! So it's old math. Like, you guys know this stuff. You know how to get, if it's plus 22 to subtract it. If you're multiplying by 3, divide it. You know all these steps. There's nothing new happening today. Just some new notation with our inverse function. Yeah. So question number 3 on your not ticket out the door, just kidding. Woo, on your student activity sheet. So for this t-shirt issue, we found that the original function was 3x plus 22, and that the inverse function was 1/3 x minus 22/3. Now, I'm curious, you may have noticed these are both linear functions, and you also may have noticed that his slope was 3, but his slope was 1/3. That the slope of the function and the inverse function are reciprocals. So the question is that always going to be true for linear functions? Are they always going to be the inverses of each other? So let's play with the slope-intercept form of the function. You know this guy, y equals mx plus b, m is your slope, right? You know this. So first thing I want to ask you, if this is a linear function, I have 3 questions for you on number 3. Part A, if this is a linear function, y equals mx plus b, is it always going to be 1-to-1? The second thing I want you to do is you're going to want to change your y into an f of x, and then use g of x and find the inverse, just like we did on the last problem. And then I would like you to answer part C. Does this confirm our conjecture about the slopes of linear inverse functions? We notice the slopes are reciprocals. What happens after you find the inverse with those slopes? So go ahead, hit pause to work this out, all 3 of these, answer your questions, do your little bit of work, and then hit play when you're ready to check your work. So guys, if this is a linear function, as long as my slope isn't 0, it's always going to be a 1-to-1 function. Linear guys are always going to be that 1-to-1 functions, just so long as my slope isn't 0. Because of course, if my slope is 0, I don't even have a linear function anymore because I, killed it. Whoopsie. So as long as my slope is not 0, I've totally got a linear 1-to-1 function. So it should be fine. Part B, let's find that inverse. Hopefully you already did. So I changed y into f of x. And remember, the next thing we did was we plugged in g of x. I noticed that f and g canceled each other out just to give me x. And there are a few in-between steps that you may need here. So I'll go through these real quick. So you're at this point. So I subtracted b from both sides. So minus b. And when I did that, I get x minus b equals m times g of x. And of course, I need g of x to be alone. So I'm going to go ahead and divide both sides by m. And so I get, actually, I'm not going to write it again because it's already over here. Boom. So that means that I get x minus b over m equals g of x. Then I just divided x by m, and I also divided that negative b by m, and I just put a 1 on top of it, made that a 1x just to make it a little easier to deal with, and rewrote it like this. Hey. So earlier, our slope was m, but when I did the inverse, my slope is 1 over m. So yeah, guys, it looks like whenever we're doing a linear function and its inverse, let me get all that out of the way. Whenever we do the inverse of a linear function, the new slope is the reciprocal of the original function, of the original slopes function. Slope of the original function? Yeah, I can get there. I got there. So yeah, whenever you're dealing with linear functions, the inverse function slope is always going to be reciprocal of the original slope. So that's interesting to note. Yay! Kind of validates what we were noticing earlier, and we're like, that's a 3, that's a 1/3. Wait a minute. All right. Are you sick of t-shirts? Maybe. Let's build a wall. All right, guys. Let's consider some other types of functions we've played with. We've been played with in the past. Our lovely reciprocal functions, our rational functions, right? The whole f of x equals 1 over x. The rate, which we'll call f of x, so how fast they can do something, at which a bricklayer can build a wall, varies inversely with the time x it takes him to complete the wall. So f of x is the rate, or how fast he can build that brick wall. And then, of course, x is the time it takes him to complete the whole wall. So you have on question number 4 on your student activity sheet this lovely table here. So I think you might have more bits than I do. I'm not sure. So basically the idea is, look, if it takes him 2 hours to build a wall, then he can build half a wall per hour. That's the rate that he's moving at. If it takes him 4 hours to build a wall, then he can build a fourth of the wall per hour. So go ahead and keep going and fill out the rest of that table. Hit pause to fill it out. Hit play when you're ready to check your work. So you get the idea, right? You get the idea. If it takes him 6 hours to build a wall, then the rate at which the speed with which he's building the wall is a sixth of the wall per hour. If he's building a wall at an eighth of a wall per hour, it's going to take him 8 hours to build a wall. And so x hours to build a wall means that his rate is going to be 1 over x wall, 1x wall per hour to build the wall. So let's keep playing with this 1 over x function. What about the inverse of that situation? So the input has been how long it takes him to build the wall, and the output is the speed with which he builds the wall. What if I wanted the inverse of that? What if I wanted to switch my inputs and my outputs? What if the time it takes a bricklayer to complete a job is a function of how fast he works? So I want to swap my input and my output. I don't want that to be the rate equals 1 over time. I want to have my time out here and my rate inside. So remember our steps in determining in determining an inverse function. First, we had to decide if it was a one-to-one function. We said that was important. Second, we need to name the inverse function, which we've been calling g of x. Remember, the third step was we found the composition. We plugged in g of x. We noticed that f of g of x, the f and the g, if they're inverses, will cancel out to give us x. And then we worked to get g of x all alone. And then, of course, we use function inverse notation. That whole f looked like -1, but it's inverse of f notation. So here's what I would like you to do. Question number 5. Can you find the inverse of this function? You might want to graph it first. You can use Desmos if you have to. That's fine. But I'd like you to find the inverse of this function on number 5. Double check that it's a one-to-one function. You might want to make a quick note about the domain and the range, see if you notice anything, and then go ahead and do the work to find the inverse of the function and see if you notice anything interesting about the function and its inverse. So go ahead and hit pause to work out question number 5, and then hit play when you're ready to check your work. All right, let's see how you did. So first thing I did is I graphed it. And I was like, hey, here's my graph. So I graphed it right off the bat. And I was like, if I were to draw a horizontal line anywhere here, it's only going to touch once. So this is totally a one-to-one function. If you remember from our unit on rational functions, hopefully you're noticing, oh yeah, that's right. X can't equal 0. Actually, I'm going to come back here for a second. X can't equal 0, y can't equal 0. So my domain is all real numbers except for 0. My range is all real numbers except for 0. Although this is a bricklaying situation, so I guess their x and y are both going to be positive anyway, because I don't know what negative walls look like. Not real sure what a negative speed on building a wall would be, but hey, that's okay. It's how it goes. So the reality is we're only going to use positive x values for this situation. And of course, it means I have a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0. This is a one-to-one function. Yeah. So let's find the inverse. I'm going to plug in g of x. Oh, bam. Oh, sorry. Charlotte's here, and she's trying to get in on the video, but she doesn't realize they can't see you. So plug in g of x. Remember that f of g of x, f and g cancel, and you just get x. I'm going to multiply both sides by g of x. So that cancels out. And then divide both sides by x to get g of x all alone on his own. And use my function notation, the inverse of f. Hey, the inverse of my function is the same as the original function. Oh my goodness. Seriously? Yeah, seriously. So for question number 5, it turns out that the inverse of 1 over x is 1 over x. Yeah. That obviously doesn't happen all the time, but it's kind of interesting that it happened here. Question number 6 is asking you for a few things. So question number 6 is asking you to graph this function. We already have it right here. You're welcome to take a moment to hit pause and graph it for number 6, and then I'm going to show you the cool stuff we're going to do with it. So just take a moment to pause and graph the function f of x equals 1 over x, and then we're going to play with it. So go ahead and hit pause, work it out. All right, so hopefully you've graphed this function on number 6. But I'm going to show you something cool. Are you ready? Are you ready? I'm going to show you something cool. If we had patty paper, which we don't, maybe you do at home, but I don't here. We're going to trace this graph. We did this in an earlier lesson, but we're going to do it again here. So I'm going to trace the graph. I'm not going to put any labels on it. I'm not going to put my x-axis, label my x-axis or my y-axis. I'm just going to trace it. And patty paper is this kind of cool, like see-through-ish kind of paper, so you can fold it, you can flip it around, all that. Now, do you guys remember how we said early on in this unit, we were pointing out, and this is not going to be the best line I've ever drawn, we were pointing out that functions that are inverses of each other are reflections over the line y equals x. So watch what happens here. Let me bring my arrow back. Boom. Sorry, my line got all distorted, didn't it? So let's erase my line after all that. Of course, if we fold it over that y equals x, then you'll notice that you actually end up folding it right on top of itself, that it's symmetrical over that line. So if we were to actually take our function and reflect it over the line, so we're going to flip it and reflect it over y equals x, we actually ended up with the exact same function. So graphically, you can see that 1 over x its inverse is also 1 over x. So this is an important thing to remember, that a function and its inverse are symmetrical over the line y equals x. If I were to draw a diagonal line down here, the left side should be reflected on the right side, or the upper left over the lower right. So with this in mind, we're going to go over to question 7. I've got 2 of these here for you, and they were nice enough to draw that y equals x line on there. Boom, boom. I want you to tell me, are all rational functions their own inverse? This is what we're looking at. So here I have 2 graphs for you. Here I have y equals 3 over x. Is this guy gonna, if I were to flip it over the line y equals x, is it going to be symmetrical? Is it going to be its own inverse? I want you to do that for y equals 3 over x, and I also want you to do it for y equals 1 over x plus 2. So go ahead and hit pause to answer both of these, and then hit play when you're ready to check your work. So this first problem, if I were to flip it over this line, it's actually perfectly symmetrical. You can see I can fold those curves right down this line. They're going to fold right on top of each other. So that means for f of x equals 3 over x, its inverse is also going to be 3 over x. What about this one though? Y equals 1 over x plus 2. Is that symmetrical over the line y equals x? Can I fold it and make it match perfectly along that line? Well, no, I can't. So because it's not symmetrical, that means that it's not its own inverse. It doesn't mean it doesn't have an inverse. F of x has an inverse, but its inverse is not going to be 1 over x plus 2 because it's not symmetrical over that line. If I were to reflect it, it would not look the same. So now that we've established, hey, this guy has a different inverse, let's figure out what it is. Go over to question number 8. So I would like you to find the inverse of f of x equals 1 over x plus 2. I would like you to plug in g of x and solve for g of x and see what you get. So go ahead and hit pause to work this out and then hit play when you're ready to check your work. All right, so the first thing I did is everywhere I saw an x, I plugged in g of x. And then, of course, f of g of x, we knew that f and g would cancel because they're inverses. So I just end up with x equals 1 over g of x plus 2. I multiplied both sides by g of x plus 2. So I took this whole thing and I multiplied it by x so that I could get it off the bottom. And then I divided, I didn't want the x over there. I'm trying to get g of x alone. So I divided both sides by x. So I have g of x plus 2 equals 1 over x. Need to get g of x alone, so I'll just subtract 2 from both sides. So now I know that g of x equals 1 over x minus 2. And of course, we can also use our new notation that g of x is actually the inverse of f of x. So I can use my inverse notation here as well. All right, I got one last thing for you guys. Question number 9. Now that you're getting the feel of this, now that we've keep plugging in g of x in order to find the inverse of the function, I want you to do it one more time with question number 9 on your student activity sheet. So go ahead and hit pause to work this out and then hit play when you're ready to check your work. All right, let's plug away. So I'm gonna plug stuff in. So I'm going to go ahead and plug in, instead everywhere I see an x, I'm going to plug in g of x. So I'm going to say f of g of x equals 4 over g of x minus 2. I know that f and g over here are going to cancel each other out because they are inverses. That's why we did it. So I'm going to say x equals 4 over g of x minus 2. Here we go. Change up the color a little bit because now I'm going to multiply both sides by g of x minus 2. So I don't have that in the denominator anymore because that's super annoying. So multiply this side by g of x minus 2. So those will cancel out, which of course is why we did it, which means I'm left with x times g of x minus 2 equals 4. I don't like this x on the outside. He's causing me some problems, causing me some grief. So I'm going to go ahead and divide both sides by x. Do it to one side, you got to do it to the other. You know how it goes. And then that leaves me with g of x minus 2 equals 4. And I can take that a step further. Yeah, I'm all right. Take that a step further and I can go ahead and add 2 to both sides because again, the whole point of this is I'm trying to get g of x alone. So plus 2, which means I end up with g of x all by himself. And we said let's use our fancy inverse notation, inverse of f of x. And we have just found, sorry about that. We have just found, oh, sorry, I made a mistake. Hang on, because that should be over x, shouldn't it? There we go. So I now have 4 over x, and then I have a plus 2. Wow, I'm losing things. Don't lose your x. In fact, I'm going to erase that and make it prettier because it's freaking me out. I'll try that again. Shall we try that again? So that's supposed to be over x. And then I'm going to do the little plus 2 out here. Right? There we go. Is that better? Sorry for my sketchy handwriting. My bad. All right, guys. As always, I hope you found this helpful and I hope you found this useful. If you got questions or concerns, please feel free to email me or come see me during office hours. I'll talk to you later.